When an AI agent mishandles an order or request, the first thing that we think of always to blame the model. But often the real failure could be a tool call we never saw or a slow inventory check, a backorder sub-process that we couldn't print or debug. In this video, we wire a flight recorder into the full stack. So CrewAI, Ollama on one side, MCP tools over stdio on the other, and OpenTelemetry, so every LLM round and every tool call shares one trace ID across processes. We will build it live, line by line. At the end, we run the incident demo and open Jaeger. You will watch the water flow go from the agent thought through the MCP get order, check inventory, to the exact span that turns red. If you have ever wanted to see inside an agent instead of guessing, stay for the Jaeger UI. So here what we are building. A small incident response agent. A customer complain about a specific order. CrewAI drives a local llama model through Ollama. The agent does not fake the answer in Python. It calls a real MCP tool, look up the order, check inventory, optionally notify Slack. Those tools live in a separate MCP server built with FastMCP. CrewAI spawns it as a child process. They talk over std-in and std-out with JSON messages only. That is the MCP, the Model Context Protocol in practice. The interesting part is observability. We use Logfire on top of OpenTelemetry. One shared setup module configures tracing for both processes. Logfire instruments MCP so trace context crosses the stdio pipe. The same trace ID in the agent and in the server. CrewAI and LightAM instrumentation add workflow spans and LLM spans with prompts and replies when we want them. For export, we keep it free and local. Docker Jaeger on port 16686 for the UI and the port 4318 for OTLB HTTP. No Logfire token required for this demo, but we have the implementation ready for the Logfire cloud. We will type 4 areas. An OTEL package acts as an API for the configuration of the telemetry packages, the FastMCP incident server with 3 tools, the CrewAI agent that connects it and orchestrates everything, and a short Docker compose for Jaeger. When the code is in place, we run the demo script, then we switch to the browser and read the trace together. Now we will start with the OTEL package. We will start by creating our OTEL module, OpenTelemetry module. We will create a package folder. Then we open setup.py file. We will have this empty init file, so Python treats it as a module. First, we import the OS because we read environment variables a lot and we set default with the setDefault function. First, we define the function configure telemetry. We have the service name, which is required. It becomes the OpenTelemetry service.name resource attribute. We will see later on when we configure the OpenTelemetry for Logfire. But this one is important because in Jaeger, you will filter on crew incident agent, for example, versus MCP incident server. These two services or modules we will create it later. They have the same trace ID, but they will have a different service name. And then we have the instrument crew. This should be defaulted to false. Only the crew incident agent should set this one to true, so we can trace everything related to the CrewAI and LLM interaction. But for the MCP server, we don't have any kind of CrewAI orchestration, so we have to set it to false. Otherwise, we will see a noisy warning in the log. The stdio safe should be defaulted to false. We will explain more about it later on. But in short, this field will tell Logfire to not print any kind of tracing line to the std-out, because the std-out is reserved for MCP messages. And this will be the case for the MCP server. But for the crew agent, we will see that we can set the stdio safe to false because it doesn't matter that much. So we have here a doc string for this function, configuring the tracing for MCP. We start by importing the Logfire module. we don't import logfire module at the top of the file. The first reason for me is importing logfire at the module level can pull in a large dependency tree as soon as anything does import otel.setup, even if the process never configured tracing. And also when we come to the environment variables later on for the OTLB, this must be set before the logfire.configure run when we are using the local Jaeger. Keeping the import inside the function makes the order obvious. So first we read the token, so maybe we set the OTL environment variables, then configure it. So then we get the first environment variables is a logfire token, save it in the token variable. The trick here that if we didn't find a token, so if we didn't set a token for our application, we need to depend on the local Jaeger instance. And for that, we need to set some default environment variables to tell the logfire that we need to forward all these logs to the internal or the local Jaeger. So first we need to set the exporter OTLB protocol to HTTP protocol buffer. And the reason for that, if we need to use a logfire cloud, so we use HTTP there. So we just need to make everything compatible with the HTTP protocol. Otherwise, the Jaeger has the option also to configure the gRPC protocol. And this can be configured when we set the default for the exporter OTLB traces endpoint and change the port number to the one that is compatible with the gRPC. So now here we are putting it 4318, and this is the one that is compatible with the HTTP. If we flip the port to 4317, for example, which is compatible with gRPC, I think we will see some kind of errors from Jaeger that it cannot be configured. So now we will keep the protocol as HTTP and we keep the port as 4318. And we need to set the matrix exporter to none. This will tell the logfire that we don't have any kind of matrix backend. We will not have any kind of matrix backend. So we don't have Prometheus or something that collect all this kind of matrix. Otherwise, we will see a lot of warnings in the logs. And here we come to the main function from logfire. So we have the logfire.configure. We need to pass the service name, which equals to the parameter we passed in, the one that will be differ per process. We will have two processes, the crew agent and the MCP server we will implement later. So the crew agent will have a different service name than the MCP server. And the second parameter sent to logfire. This is important just to tell logfire that we don't need to send anything to the cloud, or we tell him that we need to send something to the cloud. So send to logfire will depend on the token. So if we have the token, that means we need to send the stuff to the cloud. If we don't have the token, then we just keep everything local. And then we pass the token, and then we will have the console. And here we will explain a little bit about the stdio safe that we pass to the configure telemetry. So the logfire does two different things. First, it sends traces to Jaeger that keeps working no matter what we set here. Second, it can print friendly tracing lines in your terminal. That printing uses stdout. The crew agent process, when we set the stdio safe as false, the console will be none in that case. So logfire may print tracing line in the terminal. And the reason for that, because nobody else is listening to the stdout, so it's harmless. But when we have the MCP server process, we must set the stdio safe to true, and this will set the console to false. So that means the logfire will not print anything to the console, because the stdout, which is the console, will now be busy with the messages between the MCP server and the agent. The crew agent and the MCP server, they talk through stdout using JSON messages only, like a private chat on one wire. If logfire also prints tracing lines on the same wire, the agent tries to read them as JSON, which fails, and you will get a lot of parsing error in the stdout. So in short, stdio safe here means that if we set it to true, that the process is using the MCP on the stdout. So we need to turn off logfire terminal print, and the console is false in that case. Then we need to launch the logfire instrument MCP with no argument. This patches the official MCP Python SDK. So client and server request create spans, and W3 trace context is injected and extracted via meta parameters, which is called params meta. So this line actually instruct the logfire to create the spans. For example, in our case, for the MCP server, it will create all the request spans for the tools calls and everything, and also for the agent. Then we need another function to do the tracing for the CrewAI and the LLM. So we call it instrument CrewAI and LLM. And here we need to import the instrumentation class from CrewAI. So we need to import the CrewAI instrumenter and then call the CrewAI instrumenter.instrument. And then we need to call the instrument light LLM from the logfire modules that we'll pass on. So here we need to set the tracer provider for the CrewAI instrumenter, and we get it from the default logfire instance. We pull the tracer provider that logfire.configure just installed. So every instrumenter must share a single provider, so all spans land in one trace tree and one export pipeline. If we call CrewAI instrumenter.instrument without any argument, it may try to install its own provider, and Python may raise something about overriding the current trace provider is not allowed, and some kind of errors. And maybe in some versions the instrumentation will silently fail and you will only see MCP span in Jaeger, not the CrewAI workflow or the .llm spans. And then we can just make it as a private function here because we will have the Boolean indicator instrument CrewAI. If it's true, then we need to call this function. Otherwise, we don't need to call it. So here we need to create the second module, the MCP server incident module. We will have empty init file here to have a Python module, and then we will have our incident server.py. We will start by importing the annotations from future. Here is a conventional way to have the modern typing. Annotation will help us to avoid any kind of forward reference problems. It's not a mandatory. Then we need to start by importing the configure telemetry from our otel.setup. Call it with the service name. This time is the MCP incident server. And we need to set the stdio save to true. As we mentioned earlier, the stdio save, when we set it to true, that means we are telling the console output of our log file to be always false. So not to print any kind of JSON or data to the std out, because the std out will be busy with the communication between the MCP incident server and the crew agent. Then we need to create our app, and it will be the FastMCP app. We need to import the FastMCP from the MCP server.fastmcp. The FastMCP is the easy way to build that server in Python. So in this demo, the CrewAI is the agent and incident server will be the tool server. And they are two separate processes. CrewAI starts the server as a sub-process and talks to it over std-in and std-out using the JSON message. The FastMCP server is the easy way to build that server in Python. It ships inside the official MCP package from MCP server FastMCP. You don't install a separate MCP product. It's a class in the MCP Python SDK. The MCP will help us to create the app. If we need to create any kind of tool, we just need to decorate it with app.tool, as we will see later. Without the FastMCP, you would use the lower level MCP server class and had right handlers for listing tools, calling the tools, and wiring the protocols. FastMCP is a shortcut, decorators, and just one call for the run. So for the FastMCP, we just need to pass the server name, which will be the incident ops. And the second argument, the instruction, is just a one string abstract instruction. Like first we need to get the order, check the inventory, and then alert if necessary. FastMCP attaches that to the server, so the model, the LLM model, reads it when tools are listed, and not only from the CrewAI task text. Now we need to create our fake data. We will start with the orders, which will be dictionary. We need to get the any type here. We will have two orders. So starting with the first order, the key will be the order number. We can have just any number here, so 1842. And we will have information for that order, like the order ID, the customer, the SKU, and we will choose SKU for this order to be the delayed one. So this is the SKU that we can fire some errors and try to check if it's being fired correctly, have the product, and has the status and the warehouse. The other order will be the healthy one. So 9999 will also have the same, the order ID, customer, and SKU, and the SKU in this time will be the healthy one. For our inventory, we'll also have it as a dictionary. We will have two keys, so two SKUs. The healthy SKU, the SKU OK01, and the delayed one. So we can have some information like the SKU itself and the availability, how many pieces is available, how many is reserved, and the status. So this one would be healthy. For the delayed one, we will have the same information, but the availability will be 0, and also the status will be back order. We will add one more key called 88 days. So to mimic the status that we will be waiting for the back order to fulfill. So now it's 14 here. We will have a const for the failed SKU. We will use it later a lot. So we'll just have here that the failed SKU will be the SKU delayed 42. And then we will have 3 tools. We will have the get order tool, the check inventory, and notify Slack. For the get order, we will have the order ID as the input, and we need to start the logfire span. We call this event the get order, and we need to pass or attach the order ID to it. So the first step, we need to get the order from our DB or the fake data. Make sure that to strip the order ID. So if the LLM pass any kind of spaces around our order ID, we make sure just to get the text without any kind of spaces. So if there is no order, we need to return an error object passing the order ID and also having a message that there is no order found with that ID. Otherwise, we need to fire an event in the logfire. We call that the order is loaded, and also we need to pass or attach the order object and return a success message or a success object that we found the order and attach the order to it. For the check inventory, here we are trying to check the warehouse stock for the SKU. We need to add some kind of delay to mimic a reward scenario, so maybe slow underload. So the SKU also we need to strip it, same like the order ID. Just to have our example running our demo, we need to just check if there is any keyword that matches delayed keyword appeared in the SKU, then we just consider this is a failed SKU. It's just for our example to run without any kind of errors. In case the LLM or the CrewAI hallucinated some kind of failed SKU, so at least we can get it in our demo and see it in the logfire. But in a real world case scenario, we can't do something like that. So we start with the logfire span for checking inventory, attaching the SKU, and having the slow second attached object as 20. We fire an event for inventory lookup started and attaching the SKU. Then we need to sleep for 20 seconds, but I guess we can have the slow second as a const. We use it more than one time, so we can just have it as a const. And then getting the record from our inventory. If there is no record, then we need to return also a failed object or an object stating that we didn't find the record, a message stating that unknown SKU. But if the SKU was found and it matches the failed SKU, here we need to trigger an error event in the logfire stating that inventory backorder blocks fulfillment. We need to attach the SKU and attach the record for that SKU. Then we need to return similar message here to the none, but we need to add few more details on it. So we need to add the status and availability, the 88 days, reserved, and the message. In the message, we mentioned the SKU is on back order. Also, we can add estimated restock. We just need to have here some kind of error handling. Getting the 88 days out of the record without failing is better than direct access. And then we need to fire an info event if the SKU doesn't match the failed SKU. So if you found the record for that SKU and the SKU doesn't match the failed SKU, then we found the healthy SKU in the inventory. So we mentioned here the inventory is healthy, attach the SKU and the record or the available products from the record. And we return a success object here that we found the record and there is no error. For the last tool, it's a notify Slack. We expect channel and message as an input. So here we are posting incident update to Slack channel. We also need to start the logfire span called notify Slack, attaching the channel name, and then we will have an info event for the logfire called the Slack notification sent, attaching the channel and the message, just retaining that we sent the message, also mentioning the channel and message. After that, we need to fire up our application. So we have the main function here, and inside it the app that we created, the FastMCP app. We need to run it, defining the transport to be the stdio. This is the transport way that the crew agent will deal with our MCP server. And then if this module being called, we need to start the main function. So for the crew agent, we need to create also a module with the init file, empty init file, to have it as a Python module, and then we'll have our run incident.py file. We will start by initializing the root path. So we need to get the path of the current directory, and then we need to make sure that we set in the default environment variable this root directory with the .CrewAI. So all the temporary file or the file that will be created by orchestration layer will be saved in this directory. Also, we need to set the CrewAI tracing enabled to false. So we need to make sure that all the tracing is going to the log file. We don't need the CrewAI itself to do the tracing internally. Then we need to start. We will have our main function, and then we need to import the configure telemetry from our otel.setup and configure the telemetry. This time we need to give it the crew incidents agent service name. The instrument CrewAI this time should be true, because for this configuration, we need to make sure that our telemetry is tracking all the CrewAI and LLM interaction. Then we need to set the order ID. This will be the failed order ID to mimic the example of the error state. We need just to check what was the actual error ID and get it back here. Then we need to start our context for the MCP server adapter. So the MCP server adapter, which we will import, it's a context manager that starts the sub process on enter and stops exist. So this where the sub process for our MCP server will be started. We need to pass server parameters. So I need to create another object here for the server parameters, and it will be from the stdio server parameters. The command will be the executable Python command from sys.executable, and the argument will be targeting our MCP server. So it will be the MCP server.incident server. So this is the file that will be started as our MCP server, and then we need to pass all the environment variables that we have. In addition to the Python path, we need to make sure that it points also to the root of this project. So we will get this server params and attach it to the MCP server adapter. In this context, we will have the tools. So we just here for small validation step, we need to print all the tools names that we got, and then we need to initialize the CrewAI basic object. So we have the investigator, the agent, and I think here we need to create our LLM object first. So the LLM will be the LLM object from CrewAI. We need to import the agent and the crew, and also we will use the process later on, the task. For the LLM class, we need to pass the model. So in our case will be the Llama 3.2, and then the base URL, which will be the localhost 11434. We need to lower the temperature here, so we don't need that much creativity from the model. It will be more or less a straightforward tool calling instruction. So for the agent, it will be the on-call incident investigator. The goal is to diagnose why the customer order is delayed. So we will use MCP tools for that, making sure that to use the get order first and then check inventory. For the backstory, we need to tell few words for the agent to act calm and never guess the inventory. So always check the inventory and so on. And we need to set the remaining parameters. For the task, we need to supply the description for the investigation. So this task will be about investigating the order status for that specific order. We need to first to call the get order and check the inventory. If the inventory is bad, we need to summarize the root cause. Also, we need to invoke the tools and return a short incident summary. So as a validation step for the CrewAI, the expected output will be like 3 to 5 sentences for incident summary. Then we need to initialize our crew object with the agents, tasks, and process, which will be the sequential one, and we need to kick it off. We need to create our Docker Compose file only for the Jaeger instance. So we use the all-in-one image. The port 16686 will be for the web UI, and the port 4318 for receiving the traces over the HTTP. So this is the only two ports that we are interested on. And also we enable the collector OTLP environment variable, which turns the ingest on. So after we execute our script for running the incident, we can see that the crew agent logs already giving us some output. Going back into the logs, we can clearly see the tool input and tool output. So the tool orchestration with the MCP server is working fine. We see here that we're getting the order details for the requested order. And also we can see here that we have the investigator agent working fine, getting something from inventory and having the output. We need to check in the Jaeger UI if all the services is being traced there, and we have the traced error there. So in the Jaeger UI, if we refreshed, we can see that the crew incident agent and the incident server, the two services are available. And from the traces, we can see the error that we propagated from our script. So if we click into the interaction for the CrewAI agent or the crew incident agent, we can see all the interaction happened in the crew incident agent. And we can see from the trace here, the LLM interaction, the model is being used for the request. If we click in that interaction, we can see the details of all the prompts that has been fired by the crew agent, either the system prompt or the user prompt that is being fired by our orchestration layer. And we can see also the response from the LLM and all the other remaining parameters. Also the same, we can see it for the completion event that will be triggered automatically by the CrewAI orchestration layer, which will have all the final information about all the messages that being fired and all the responses that we received from the LLM and all the other important parameter for the CrewAI agent. If we scroll down, we can see also the tools that been called for the MCP, and we can see also down there the error or the incident that being fired by our application layer or from our MCP server. So it's about the inventory order blocks fulfillment. That was the error that we fired when we retrieve the bad SKU or SKU for a product that doesn't have availability in our stock. And see all the remaining details here. So Jaeger gives you this kind of overview for all the interactions that happen in your application. In our case here, we looked into the crew incident agent and we saw all the interaction that happened between the agent and the LLM models, and also the MCP request and the tool calls and the registering for the MCP server incident. Thanks for watching. If you want more of this, like the video, subscribe with notification on, and share it with your friends. We release new videos every week on AI development, agents, and developer tooling. Thanks for being here.